years ago when I started programming, you have to do if you want to draw circles. There were no predefined functions, so you have to do it with cycles. So at the end of this, we call again context begin. Sorry, context dot begin path, which is important to use. Otherwise, even if we change the style and we issue again a stroke command, the style of the stroking will be the latest one and will affect all the previous drawing. If we want to divide different drawing with different styles, we have to use this begin path. So let's use a couple of variables. So the first one being segments. Let's start with just 8, for example. Another one called radius, which is the radius of the circle. 100 is more than enough. A center, position, so let's say 400, and a center y coordinate. Okay, so we have basically defined how our circle, our circumference is going to look like. It will be centered at 400, 300 with a 100 radius divided in 8 segments. So first one, let's have this copied. First of all, we have to move to the center. Not exactly to the center, but on the first point over the circumference. So it is going to be cx plus radius cy. And then we need another 4th cycle. Okay. We need to compute an alpha var equal to segments math.pi is just a pi taken from the standard mathematical library of JavaScript. And then from the point we set here, we start moving over the circumference. Line 2 cx plus radius as you can guess, alpha is the angle. Okay. Then we want to set the line width equal to 1 pixel. We change the stroke style to another color, for example black. And again we ask for stroking. And this is the result. Let you copy. Of course you can try to raise the number of segments. If you try with the 16 or 74, 64 is more than enough, you will see a perfect circle with 16. The result is this one. With 64, the result is going to be a circle. I want to show you something about, after if you want to finish copying, I want to show you something about the anti-aliasing, how it works and what it is, how it looks like. Because of that, I need to comment all those lines for now. Okay. So that we have only this image. One of the interesting things working with WebGL is that the result on a canvas is just an image, is a picture, so you can save it and drop it anywhere you want. In this case, the desktop isn't good enough. Okay, let's open it with Photoshop. Anti-aliasing is that technique. There are many different algorithms for performing it, which allows to avoid that the border of the image of the lines, the border, generally speaking, the border in a CGI image looks jagged with just some steps on that. You see, it is not perfectly black, even if we asked for a black line, but there are shades of gray decided by the anti-aliasing algorithm, which allows you, when you zoom out to a more normal dimension, it looks rounded. Without that particular algorithm, this is how your line is going to look like. And of course, if you zoom out, it's not a perfect circle, it's more jagged than you expected. Anti-aliasing, of course, introduces an overhead in the computation, so when you set the graphical option for your video games on a PC, for example, you can turn on or off, or to a worse degree of precision, the anti-aliasing filter to speed up the frame rate. Okay, I think that that's enough for the 2D part. Let's start with the more interesting context, which is the WebGL one. You have seen that by calling context, we have API exposed, commands exposed, and we use those commands to draw. By changing the type of context, a different set of feature of function is exposed to us. The WebGL context is going to expose, first of all, a different coordinate system, not at all similar to the one we already see. Different set of primitives to draw, not simple as those we just experimented with, and different modes of drawing. We will see in a while in detail all these bullets. Coordinates of the drawing space. In WebGL, they start in the middle of the canvas object and extend in a normalized way like a normal Cartesian plane, with the center in 0, 0, from -1, -1 up to 1, 1. Of course, since we just have -1, 1 range, we have to resort to floating points number, which increase the byte weight for expressing each of the values. Of course, we can express values outside this range, but then we have, using some technique, to normalize all those values inside this space. And we will see how in future lesson it involves basically matrix computation. In WebGL, a primitive is simply, and this is true for OpenGL too, is just a collection of vertices. We have points in a 3D space, and we can decide and specify in which way we want them to be connected. 3 vertices in a 3D space define one plane. So the triangle defined by those 3 planes is flat. It's basically flat. It's planar. And the primitives in WebGL are 1, 2, or 3 dimensional objects. We can express single points, we can define lines, or we can define groups of triangles, which is the common way for doing 3D. In fact, all you can do with OpenGL and WebGL too is just to visualize a collection of points, lines, and triangles, and texturize or color them, or apply any illumination effect you want to do. You want them to have. That's all OpenGL is about. Any other logic, when an object is displayed, when it's not, how light changes, if the object moves, that logic is up to the JavaScript program, or, let's call it in more general way, the client code. The server code just visualize, and that's it. There are some enumerants that express how we want to use the vertex defined, which are points, we just want them to be points, lines strip, we will see in a moment the difference. Those are points, vertex 0, vertex 1, 2, 3, 4, etc. Those are lines. Each couple of vertex is connected by a line. So from vertex 0 to 1 there is a line, 2, 3, 4, 5. Different for a line strip. Line strips is the way we worked in the 2D mode. We start by positioning a vertex 0, then using line 2, we just set a second vertex connected to the first one, to the previous one, by a line, and you draw a line basically. A line loop closes the strip. Basically do the same. With triangles we have 3 possibilities. In OpenGL there are more, but those are the 3 basic. We can define each triangles by defining all its vertices, like triangles. So the first 3 vertices are connected, define a face. The second 3 vertices define a second face. Or we can have triangle strips. Vertex 0, vertex 1, vertex 2, and then they are closed by a face. Then we just add another vertex, and using the previous 2 we close another face, and so on. But it depends to the topology of the object that you want to draw. Not all objects allow you to exploit techniques like that. And the triangle fun is also a good technique to save memory by not having to store more vertices or store. Look at the triangle strip. If we use triangles, we replicate information about vertex 1 and vertex 2, because for drawing this triangle here, we always need 3 vertices, but V1 and V2 are exactly the same used by another face, so why to replicate them? Those are just techniques to lessen the memory requirement for storing extra vertices. WebGL allows the drawing of both 2D and 3D objects. We start today with the 2D object drawn by using WebGL, and you will see that drawing 2D object in WebGL is extremely complicated for the result. But the good news is that it is exactly the same difficulty that you face for drawing any complex 3D object. So once you learn the procedure, you can draw basically anything you want, provided you have the data to draw it. For example, there are differences. You cannot set directly the color of the location of a vertex to be drawn. And you cannot, of course, draw complex object by using fixed polygonal drawing functions, simply because there are too many different forms that you cannot hope just to have primitives for them. So, in some way, we have to stream to the GPU memory all the data at once, and then explain how to interpret those data in order to have the 3D object. Only at the end of this complex procedure we can call the draw call. To pass the data in WebGL, you have to create vertex buffer object, usually addressed as VBOs, that hold informations about the vertices. Information about vertices which now lose their meaning, their geometric meaning of being a vertex, just a point in a space, which carry more information than just its position. And we will see how many and which information we can store for each vertex. Position is just one of them. Then you can have a normal that specifies the direction of the triangles created using that vertex. If there are texture coordinates, if you want to paint with color, etc. So, for example, if we want just to draw a triangle in 2D, we can just provide as data 6 floating points. I put them 2 by 2 on each row just to show you that each couple is just the x and the y coordinate of a point in a 2D space. But, of course, for your program, they are just 6 floats. Then we create a VBO. GL is the context created in the canvas using WebGL as a type. We ask for the function named createBuffer, and we ask basically to WebGL to reserve a portion of memory on the GPU in which we are going to store something. That's the buffer. In VBO variable, we get the handle, basically a pointer, but the handle to that portion of memory in which we put the data. We are going to put the data. For now, we just reserve a portion of memory. Then we bind the buffer. Since we are working with a state machine, we have to specify which is going to be the buffer on which the subsequent operations are going to be made. Of course, in this case, we are just providing line by line the commands, but in a more complex code, probably the last binded or created buffer is not probably the one on which you want to operate. So you have to specify again, I want to work on the last buffer. You see, there are 2 parameters. The first one specifies which kind of array it's going to be. It's going to be an array buffer. An array. I want to put a set of values in it. And where is this buffer? Is at VBO position. VBO is the position in which we have the handle to it. So a buffer, we have data, and the data are stored on the CPU memory. Sorry, so on your client side memory. The buffer is on the GPU side, so they are in two different places. We reserved a portion of memory there, and we specify that we want to use it as an array buffer. Then we do the movement. We take things from the data variable and we move all those data inside the buffer on the GPU. The vertex data are placed. Again, we specify that we are buffering data to an array buffer. The data that we are buffering are inside the data variable, and we are going to use those data for a static draw. This means that inside the buffer, inside the GPU memory, the data that we stored never change for all the lifetime of our code. There are other drawing methods that we are not going to see for this code. Static draw is the only drawing method that we are going to use. So simply remember that with buffer data, the fourth step, we send the data there on the GPU. Now the GPU must do something with those data. And to specify how to use those data, we have to write code in GLSL, which is something quite complex, topic of a future lesson. For today, I just give you a snippet of code that you can paste in your JavaScript code, which will handle this part. We will see it into details later. The GLSL program, like the buffers, resides on the GPU memory. The client code on main memory holds anything else. So we have sent the data to the GLSL, to the same memory in which the program resides, the GLSL program resides, in order to obtain the rendered image. But up to now, we have two things on the GPU memory. We have the data in a buffer, and we have the pipeline program in another part of the memory. But the two things are not communicating right now. Then we have to issue, again, on the main code, we have to open some communication channel between those two parts. So the GLSL program must be written, compiled, and then we have to get information from the compiled program. So first of all, we retrieve the pointer, the handle, to the location on the GPU memory where we have put the code, the input data. Then we enable the communication between the two parts. Usually this is not open by default. And then we send to the program, so from the buffer in which we have the data to the compiled GLSL program, we send the data. Vertex position, probably this part will be more clear later on, but our first GLSL program just works with vertices. Vertices, thus vertex data, are the input of our program. So we can collect the point, the handle, to the point of memory where our program expects to find the data we send it. And we store this new handle in vertex position handle. This is the position in memory where we have to send the vertex data in order for the GLSL program to find it and use it. Enable is just required, otherwise it won't work. But then we send the data, and we send the data to the input vertex position handle. We specify that each vertex is defined by two floating values, by two data elements The data elements are float values, and this is important because we are working on memory. So if, for example, we say int, an int is of different size in bytes with respect to the float. So we are not going to collect exactly the value that we want. We are operating with memory, we have to specify this. False just mean that the values does not require normalization. And the last two values, I left them for a future lesson. Okay, at this point, finally, we can call the drawing function. In this case, we decided to create a line strip. We have 3 vertices, so starting from the 0 element of the set of data up to the 3rd one, remember that even if we pass 6 values, we couple them 2 by 2, so they define 3 vertices here, from 0 to 3 and close, and we have a triangles, which for drawing a triangles is a lot of effort. But consider that this procedure works for any object that you want to draw. That's the good thing. Okay. So we can try now to draw our first WebGL code. So first of all, this is not longer required. Okay, index HTML is not going to change. It's basically exactly the same. We don't need to make it change. What does change is in drawing. Of course, all these things are no longer of any use. And we need to set some global value, like for example, canvas is going to become a global variable. And instead of having context, GL is better because it's faster to type and more closely related to what we want to do. Okay. Canvas basically doesn't change. We just collect from the main document the canvas. So this is exactly the same. Instead, we want to surround with the try-catch function the part concerning the get context. Of course, no longer WebGL, no longer 2D, but WebGL. But since we don't want to have any issue with older browsers, we also accept the experimental WebGL. We try to catch any error that may arise here by simply logging them on the console. At this point, so if JavaScript was able and your browser was able to provide context WebGL context or an experimental WebGL context, GL is not going to be null any longer, but instead it has the exposed set of WebGL function. So in the if here, if GL is not null, we can put all our logic in this part. Otherwise, logging, again, maybe an alert at this point. Okay. No error. It seems that everything is working up now. So let's try to do those 8 steps that we have seen on a slides. First of all, let's create some vertices. It's going to be an array with some elements. For example, we are providing normalized values to avoid any issues on that. Let's try with 5. The last one, no commas, no comma for the last one. As you can imagine, usually those data are collected from an external file when you have a complex 3D object or just a 3D object. You usually don't have to type the values of each of the vertices of a complex figure on your own. That's why programs such as Maya or 3D Studio, Rhino, etc. exist, to avoid you to type vertex by vertex all the topology of an object. Then you export in any file format your model, and you need in your code something able to decode that file format to produce a list of floating points like this. Then, after this decoding, you can use all those values to visualize in any way you prefer to do that. Then, let's create the VBO gl.createBuffer. Then we bind the buffer, and it's going to be an array buffer, and then we stream the data to it. One of the bad and good things about JavaScript is that it is not too much picky about the types, variable types. Sometimes this becomes an issue. In this case, it's better to type vertices not just a generic object, but a collection of float points, float values. So we say convert to float32 array the content of vertices. Those are the data that we pass, so we are sure they are in the right form. And the goal is to have a static goal. Okay. Those are the first three operations that we need to. Let's see if it complies. Not complying. Okay. At this point, we should insert the GLSL part, which for now you can download from the BEAT website in the section concerning this part of the course. It's going to be a file like this one, very simple. So for now you have to take it for granted. This is the part. In two variables we hold the code, the GLSL code. We then create a program. We compile it with some step of function. We link it, and in the end we add an handle to the portion of memory in which the program exists inside this variable, which is program. And now we say to OpenGL that we want to use that program, meaning an OpenGL program, of course. From the program we collect the position of its expected inputs using var vertex position handle. Maybe it's too long as a variable name, but just to be clear what's about. And in order to collect the input position, we have to use this function, which I'll explain next lesson, get attrib location. Position 1 is the name of a variable inside the GLSL code, the variable that we want to use as an input for the GLSL code, and we have to bring it out the memory, the GPU memory, and bring it inside the client range of action. Then we just enable the communication between the buffer and the program. Enable vertex array. It's very easy to make typos of those long names. So now the buffer and the program are communicating. It's open the communication between them, and we send the data in the buffer to the program using GL vertex attrib pointer. Okay, let's see. And in the end we have the drawing call. Draw arrays, because we are drawing from an array of data. Let's start with gl.points, starting from 0 up to 5, because we have 10 floats coupled. And let's see if we are lucky and something happens. No, there's an error. Okay. Okay. 6 Oh, I forgot something. Okay, 44. Vertex position to float. Yes, there is a false. Okay. Now you see, probably, I hope you can see them. You see, we were able, with a lot of effort, to draw 5 points over our canvas. But the interesting thing is that we don't have to use those values just as point. Instead, we can, for example, transform them in lines. The number is not even, is odd, so you see that no longer we have points, but we just have 2 lines, because we expressed 5 vertices, 6 were required. OpenGL, WebGL was unable to draw the last line. Or we can, for example, comment this one and instead use a line underscore strip. Pretty obvious because it just uses the next vertex together with the previous one. And we can also close it. Instead of having a strip, we can have a loop. And in this case, everything is complete. But the important part are triangles. They are the basics of 3D visualization. So let's see what we can do with triangles. With triangles, sadly, we can just have one. We miss one vertex. Same thing can be done again. This time, instead of triangles, we can have a triangle strip. And now we have something more complex. There is one triangle that uses the first, the second, and the third vertex specified. Then we add a vertex here, but we keep those two for the strip. So here we have another triangle, which covers the first one and is covered by the third. And then using those two vertices here, adding a third one, we have a third triangle. If we want to close the geometry, we have to use triangle fan. By making extra triangles, it will cover all the area, because it will keep the first one as one of the vertices for each of the triangles. So 1, 2, 3, and the last one, 3, and that's it. Okay, so this is it. I think that for today is enough. There was still one thing about aspect ratio, but we can see about it next lesson. I don't know when next lesson will be. I left my agenda somewhere, I don't remember where. And I think that for today is all. Thanks.